All right.
Hey,
What's
hey,
up, Mr. Wing?
what's happening? Here we are.
Nothing. Back at it again, buddy.
I see we're
12.3.
I see we're still talking about acids and bases. I thought we did that last video.
Whole units, acids and bases, buddy. Beautiful thing.
Oh, I
Let's
wanted to
see.
tell you, did you see the last video Brielle decided to come in?
Mm-hmm.
She decided apparently that she wanted to draw with marker all over her body. So she had like marker on her face and it's all over her. And
Oh, man. Kids are great.
Allie was trying to do a couple emails and left her alone for 5 minutes and boom.
That's how kids learn. It's a beautiful thing.
The good news is it was all on her body and not on the walls.
That's a win. And it wasn't Sharpie, was it?
Nope, it's washable.
There you go. Just like putting a bath bomb in the water. Just turns the water a different color. It's a beautiful thing. Man. This one's a quick one, Mr. Wing.
Okay, let's get it started.
12.3. After this one, they're basically halfway done with the last unit that they have to learn in chemistry. So that's an exciting time for most kids. Let's see how we go. So this is the concept of pH. Everybody's heard of pH, right? Everybody's heard of pH. They just don't know exactly what it means. They know kind of, it means it's more acidic or more basic or whatever, but that's all they know. So let's go through it. And this is a quick review of what we already learned. Remember that water was amphoteric. Remember that? So that means it can have an acid and a base. So let's show what can happen if we have two water molecules together in the same water bottle, right? A big, gigantic jug of water. We can have some of them act as an acid and donate, and some of them act as a base and accept. So water, since it can do both, can actually act differently within the same jug of water, same bottle of water. So here we have this one being the acid, this one being the base. So, Mr. Wayne, what would be left of H2O after it donated a hydrogen ion?
Hydroxide.
Hydroxide. And what will this water become after it accepts a hydrogen ion?
H3O called hydronium.
All right. So that's what we end up getting here, right? So if we were to do our KEQ for this with the law of mass action, would we include these waters in the law of mass action?
I believe that I remember that we decided that the only things you can include are aqueous solutions and gases. So
Right.
you would not include them because they're liquids.
No. So we would not include those. So if we look at the KEQ here, bring all this up, the only thing we would have would be the products over the reactants, but since we don't include the reactants, you just have the products here. So the KEQ is equal to the concentration of H3O plus and OH minus after it reaches equilibrium, okay? Now that's called now, since it's the KEQ is now dealing with water, we call that the KW instead of KEQ. But it's the same thing, same exact concept here. And at 25 degrees Celsius, look what the KW is for that, Mr. Wing. Look at that. Is that a big or a small number?
That's a really, really, really small number.
Really small. So if we have a really, really, really small K value, which is more heavily favored, the reactants or products?
The reactants.
The reactants. So when you drink a bottle of water, almost all of it, there you are. Good example, Mr. Wing. Almost all of it is going to remain as water. Only a few tiny particles will actually become the hydronium ion, which can burn your face off, and the hydroxide ion, which can burn your face off. So these are very, very small concentrations after this has reached equilibrium, which is why it's still safe to drink water. But we need to use this equation to our advantage. What?
Yeah, I just want in all water that is happening. You can't see it, but there are a few hydronium and hydroxide ions in this water right here.
That's right. In fact, if it's good water, these should be equal, so it'll be neutral, right? Because this makes things acidic, this makes things basic. They should be equal. Now let's move on and check it out. Why we're going to use this stuff? Well, sometimes we now know that we have this. And what if we were given one of these? We know the KW is 10 to the negative 14th. Can we find the other one? They're going to ask you questions like that. So a lot of chemistry classes want to ask questions like this. So here's a typical question that has, calculate the OH minus ions if the H plus, I use H plus there, Mr. Wayne.
Oh.
What's the difference? Is there a difference between H plus and H3O plus?
Nope, it's the same exact thing.
Same thing. These are exactly the same. Do not forget that, okay? So if the H plus or the H3O plus here is 4.5 times 10 to the negative fifth, they wanted to calculate this and then talk about whether it's an acid or a base. So here's the equation setup. Kw is equal to the H3O plus times the OH minus. How are we going to solve for OH minus? What do we do, Mr. Wing?
We're going to divide both sides by the 4.5 times 10 to the negative fifth to isolate the OH, because this is a 3-variable problem. So you have to you solve for the missing variable, and
there you go.
boom.
Now,
We see
they better learn how to put that in their calculator correctly, right?
they know.
They better use that EE button, because if they use that times 10 to the negative fifth, they got to make sure they put everything in parentheses or it will not go well for them, okay? So how do we know whether this is an acid or a base? I know this makes things more acidic and this thing makes things more basic. So if they were equal, it would be neutral. So all we got to do is compare this one and the one below. Which one's the larger number? Is it the 4.5 times the negative fifth or 2.2 times the negative 10th?
Definitely the 4.5 times 10 to the negative fifth. That's going to have less zeros in front of it than the other one. So because that is a large one, that's our pH. So
So that's going to prove whether it's an acid, right?
yeah, that's because it's bigger. We know that it's an acid, which is going to have a lower pH.
There you go. So this is a larger number, so that's going to be why it's an acid. If this would have been larger, it would have been a base, but that's what he got. Let's get into the concept of pH, Mr. Wing. I'm excited for you. Okay.
Yeah, I got a little ahead of myself there.
That's all right. That's all right. You know what's coming. pH and pOH. I want like the key we got to remember is these little p's right here. So whenever a little p is used in science, it means the negative log base 10. So whatever the number is, you just take the negative log base 10 of it, and you've got a little p right there. So for example, if we have pH right here, that's the negative log base 10 of the H, or the H3O plus. Remember, those are the same thing. And the pOH would be the negative log base 10 of the OH minus. So just that little p means to take the negative log base 10 of whatever is after the little p right there. Okay.
Remember that the H3O plus and the OH that are in the brackets, that's going to be the concentration. So which is the molarity. So those are usually pretty small numbers.
Yeah, like you get a 2 molar, 3 molar, 0.5 molar, something like that. We're not going to get much more than 2 molar, so maybe 4 molar. So let's check it out. Remember that Kw is equal to H3O plus times OH minus, and that equals 10 to the negative 14th. Well, if we take the negative log base 10 of this 10 to the negative 14th, essentially that's asking us what is the negative of the exponent if the base is 10. So that means that the pKw is equal to 14, all right? So think about it, that's the negative of that exponent if the base is 10. So pH plus pOH has to equal 14. So now it makes it easier. If I give you the pH, and you can find the pOH very quickly. So for example, if pOH is 8, then the pH has to be 6. They have to add up to 14. Just like these two have to multiply by each other to equal this number, these two have to add up to each other to eat up that, right?
So yeah, so I think a lot of our students probably know, Mr. Worth, that the pH scale goes from 0 to 14, but now they can have a better understanding and appreciation for why it's at 14 and not 25 or 52.
Yeah.
It all is based on this Kw value.
Yeah,
and
Kw, which is basically
another thing.
Equilibrium they learned.
Yep. And the other thing is it has to be at a certain temperature. So 25 degrees Celsius is about 77 degrees Fahrenheit. So I just kind of want to point that out, that we have to keep our a consistent temperature as well.
Yeah, because this is not 10 to the negative 14th if it's not at 25 degrees Celsius. But in this class, they're always going to be 25. We're not going to mess with you, okay? All right, so moving along, here's that pH scale you were talking about, Mr. Wing.
Okay, so yeah, I feel like you guys have seen this a lot. So how we're going to use this is basically just to find the pH if you're given pOH or vice versa. But just know 7 is neutral. It's going to be green in color. If something, here's a word, alkaline. We're going to use alkaline similar to base. They mean the same thing.
Yeah, that's why we had alkaline earth metals, right?
Alkaline earth metals were all, remember they turned blue And so we remembered that blues were bases for that lab. But anyway, acidics are going to be like the lighter colors, the reds, pinks, and orange.
Yeah, not the color of the chemicals. That's
No,
the color they turn universal indicator.
yeah,
But yeah, like anything below seven's an acid, anything above seven's a base. This is what a universal indicator turns the colors of. But you might have seen like litmus was blue and for bases and red for acids, right? All right, so let's
yes,
talk about this stuff right here, Mr. Wing. When H3O plus is equal to OH minus, would that be neutral?
yes,
Yeah, that's neutral. So doesn't that mean that the pH is also equal to the pOH, right?
yes,
So if I took the negative log of this base 10 and the negative log of this base 10, they would also be equal to each other. So if pH is equal to pOH and pH plus pOH has to equal 14, they both have to equal 7. So that explains why neutral pH is 7, right? And if we have pH below 7, it's more acidic, and above 7 is more basic. I think that's all you need to tell them about that, right?
yep.
Nothing crazy. All right. So now let's talk about a couple of example problems with these kids. Um,
All
and
right.
is there one or two of these right here?
And there's two.
Okay. You want to hit this one?
So
I'll hit the next one.
sure.
All right.
Suppose a solution came to equilibrium was found to have a concentration of hydrogen ions 3.2 times 10 to the negative fourth molar. What is the pH? What is the pOH? And then we got to figure out whether the solution is acidic or basic. So the first thing we want to do is determine whether it's or what the pH is. So we just learned that the pH is equal to the negative log base 10 of the concentration. So you're going to put in your calculator negative log.
How do we know this is pH that we're calculating, not pOH when we take the negative?
You have to identify that it's talking about hydrogen ions.
There you go.
And the hydrogen ions are going to tell you that it's the pH and not the pOH. If it said hydroxide ions, then we would have calculated the pOH.
Good. So we calculate the pH first. I always think it's easier to calculate the pH first because I just plug in my calculator, then boom, and then I got something easy to work with. So if that's the pH right there,
So now we have
go
pH.
ahead.
So this is beautiful because once we have the pH, we just have to subtract that from 14 to find the pOH. So 14 minus 3.49 is 10.51. Now, we are used to determine whether the solution is acidic or basic. We will just use the pH scale because we are all familiar with that. There is a pOH scale, but we'll just worry about the pH scale. So because the pH is less than 7, it's going to be considered acidic.
There you go. That's pretty simple, huh? So I always think it's easier to find the pH and then just compare it to the pH chart, right?
Yep.
I think because this is a much easier number to work with than this crazy stuff. So I like working with these things that are above 1 and things. So.
And on your guys' cheat sheet, we have all this at the very bottom. I think it's on the back side with the negative log stuff. I think we fixed it. The last year we forgot to put the negative in front of the log. So double check your cheat sheet. Make sure it says negative log base 10.
Yeah, good call. All right, let's do the last problem and then they're done for the day, right?
That's it.
All right, I think this is it, isn't it? So it says, what's the concentration of hydrogen ions in a solution that has a pH of 8.4? What we're going to do here is we're going to do what we call the inverse log, I think is what it's called. And all we're going to do is it's essentially this right here. If you want to know the hydrogen ion concentrations, it's just 10 to the negative pH. It's the exact opposite of what we did to find pH. Instead of taking the log base 10, we're actually taking 10 to the negative pH. So if I know the pH is 8.4, I just take 10 to the negative 8.4 on my calculator, and my calculator tells me the answer. So that's my, look at that, Mr. Wing's got a nice example there, okay? Is that your log button you're trying to show us?
I'm trying to show them the 10 base 10.
Oh,
there.
Yeah, there it is. Yeah,
It's right there.
they probably used that before when they were trying to put this in, right?
And the log is under it, so you got to hit Control Log.
Okay. So that's the concentration of H3O plus ions. Now think about it, if we wanted to calculate the OH minus ions, we could do it 2 different ways. We could subtract this from 14 and give us the pOH, and then do the same thing with this. But there's all kinds of different ways that you can do all these things. It's beautiful. But I think that's the last slide, Mr. Wayne. So
Yep.
We are done for another day. And I guess I'll see you tomorrow, Mr. Wayne.
Sounds good. Don't forget to check the questions and answers page and the doc. If you guys have questions or email us, we're glad to help.
Yep, absolutely. All right,
See
see you,
ya.
brother.